Let's get started. Good afternoon, everyone. We are going to start the afternoon session with a very exciting topic and a very exciting speaker. I have a great pleasure to introduce Dr. Mohammed Ismail, who is an associate professor at Tennessee Technology University. He's also the director for a center that's called Cybersecurity Education, Research, and Outreach. That covers a big range of things. He's a director for that big center. And I met Mohammed at an SFS PI meeting. So by now, everybody knows SFS. Those of you who will be starting in the fall know it. And he was one of the speakers there and talked about emerging technologies in cybersecurity and what this program focuses on. And I was impressed with that, and we had a long chat afterwards. So I had two things in my mind: invite him to give a CySER seminar, and maybe see if he would be available to give a presentation on a CySER summer workshop. I got a yes for both of them. So he did give a CySER seminar last spring, and what he talked about was in his area, power, and gave an excellent introduction to it. And the last 10 minutes or so were on quantum computing. I was very eager to hear, and he did a good work. And then I knew what the topic for the summer workshop should be, and he will be talking about quantum computing. The background everybody has here, Mohammed, is zero quantum computing. So assume that, and you can do what you can in the next 40 or 45 minutes. And we are running a bit late behind because we were having a field trip to a local company here that you probably would know, SEL. And we had only 45 minutes to get back from there, grab some sandwich. And so you've got a very, eager audience waiting for you. Thank you very much. And the floor is yours, and you can take it away.
Sure. Thank you, Asifau. And hello, everyone. Good afternoon. I am, as Asifau said, I'm Mohammed Ismail. I'm the director of CIROC. That's the Cybersecurity Center at Tennessee Tech. It looks into cybersecurity education, research, and outreach. And regardless of how the title look like, we are going to talk about quantum networks and how they can facilitate security, improved sensing, improved communication networking. And we will, assume that you know nothing about quantum, and we will take it from there. I'm not sure how much you'll be able to cover from the presentation, but I promise you will get out of the talk with something useful. So I will talk to you a little bit about Tennessee Tech and CIROC, just for you to know what we are doing and where we are and the research team. But then we'll talk about the preliminaries of quantum. So as I said, I assume you don't know anything about quantum. So start what's a qubit, what's a quantum gate, what's a quantum circuit, what's quantum computing, and then what's quantum networking and communication, and we take it from there. Okay. So as Asifau said, I'm from Tennessee Tech University. So Tennessee Tech is in the city of Cookeville. And the city of Cookeville, actually, it has a very nice place, which is in the middle, or roughly 1 hour, 30 minutes from 3 major cities: Nashville and Chattanooga and Knoxville. We are also roughly 1 hour and, let's say, 40 minutes from Oak Ridge National Lab. And that's why we collaborate a lot with Oak Ridge National Lab in research topics. We have their scientists doing their graduate studies, master and PhD at our university, and we work a lot with Oak Ridge National Lab. The largest college in the university is the College of Engineering, and the largest department is the Department of Computer Science. And this is the home of the cybersecurity concentration, and that's why CIROC is working closely with the Computer Science Department. Now, the CIROC, which is the Cybersecurity Education, Research, and Outreach Center, it was virtually opened in 2015 and received its designation as a National Center of Academic Excellence in Cyber Defense Education by the NSA. And then it got its physical location in January 2016. And then only last year in October, we moved to the new engineering building, which is Ashraf Islam Engineering Building. So this is now the location of CIROC. CIROC is the home of 2 prestigious programs. One of them is the NSF Scholarship for Service program. That's the NSF Cyber Corps. So since the program started here at Tennessee Tech in 2016, we had 61 SFS scholars. And this places our program among the top 10 in the nation in size of enrollment. And we are also the home to the NS3 program, which is an onboarding program for new SFS scholars. We are also a participant of the DoD CYSP Cyber Service program, and now it's called Cyber Service Academy, I think. We have been a participant in this program since 2018. This is actually the equivalent of the SFS, but from the DoD. We also hold the longest running Gen Cyber Camp in the state of Tennessee, and we do the Golden Eagle Cyber Certificate Program, which is a dual enrollment program in cybersecurity. Now, in our new location, we have space for undergrad labs, graduate student labs. We have our Cyber Innovation Lab, where we host lots of our test beds that we use for cybersecurity experimentation, and the cyber training room, where we host our workshops and cyber trainings. Our focus area in CyROC, we support education, as in formal education like IT security, information assurance, and cryptography. These are basic security courses that we support through like VMs and labs and all these kind of things. We also support like new emerging topics like quantum and AI assisted, creating the educational materials, the labs, and train the students on those. But also informal education or experiential learning, we participate a lot in competitions like CPTC, CTF, and so on. In research, we have lots of research areas, but I would say we can group them in three main themes. One of them is AI-assisted cyber physical security, where we use our test beds on power systems, drone and aerospace, and smart manufacturing to support AI solutions for cybersecurity, offense and defense in cyber physical systems. We also have another team working on quantum-enabled security, and that's part of our talk today. And our most recent group of students are working also into aerospace as in satellite and space security. In the outreach component, we do the Tennessee Gen Cyber on Wheels. We, as I said, support the dual enrollment program, and we do cyber discovery days and quantum discovery days. This is my research team. Now, this is moving from CyROC to something a little smaller, which is my research team. So at Tennessee Tech, my research team look into, as I said, AI-assisted cyber physical security and quantum technology. We receive funds from National Science Foundation, Operation Region Commission, and also Qatar Foundation. So that's about Tennessee Tech and CyROC and my research team. Now, for the remaining, because we said we have 45 minutes, so I roughly have 40 minutes. I'll, as I said, set up some foundations for quantum, and then we see, depending on our time, if we can discuss some advanced topics. So, what is quantum computing? Quantum computing, it's this like science that exploits quantum mechanical properties of matters to do calculations. So this is a different way of doing computations, okay? And it uses the concepts of quantum mechanics to do the computations. And these are superposition, and we'll talk about it in details. Entanglement, we'll also talk about it. And then interference, and we won't touch that in more details, but that's how you can get quantum computing to happen, using these concepts of superposition, entanglement, and interference to do computations. Now, how can we model quantum computing? We model quantum computing with different ways. One of these ways, which is the most, in my opinion, logical one, is the quantum circuits. So it makes sense. It's a quantum circuit, as I'll show you now. It has three components, right? You have data. So what is your data? And then what are the operations you're going to do? And then how are you going to get the results, right? And this has an analogy to classical computers, right? Your data are the bits, right? So in classical computer, your data are the bits. So you represent data as 0 or 1, right? The representation. Your operations are done through what we can call them the classical gates, right? You have something called an OR gate, an XOR gate, AND gate, and so on. And these gates are just a bunch of transistors, right? And they do the computations for you, right? So you have the classical data are the bits, the operations are through classical gates, transistors. And then you, after you do the operations, you get the results, right? You read out the results. We can do the analogy in quantum computers. So in quantum computers or quantum circuits, your data now is called the qubit. Qubit is short for quantum bit. And your operations are run through something called quantum gates. So these are gates applied on the qubits that will change, and we'll see how this will look like, change the qubits somehow for a desirable output. And then when we say we are reading out our results in quantum states, we say we do something called measurements. We're doing a measurement. So for the next couple of slides, I'll talk to you about what is a qubit, what is a quantum gate, and what does measurement mean. Okay? So as we said, the data, these are called qubits or quantum bits. And one unique thing about qubits compared to classical bits is that the classical bit, it can be either 0 or 1. But a qubit it exists in a superposition between 0 and 1. What does this mean? You can think of this as a coin, right? The coin, if you toss it, it's either head or tail. That's a classical system. So a bit representing 0 is the head, a bit represented as 1 is the tail. That's the classical system that we know. But in quantum state, in qubits, it's in superposition, which you can think of it as a spinning coin. If the coin is spinning, it's actually between the head and tail. It's something between 0 and 1. And that's a way to see, or like an analogy to think of what's a superposition, right? So you can think of the superposition as a spinning coin. It's not on head, not on tail, it's spinning, right? And so to describe this mathematically, I want a way to describe mathematically a quantum bit. We use something called orthonormal basis, right? So what does this mean? As I told you before, we have 0 and we have 1. These are the two states, 0 and 1. And then the quantum state psi here is a combination between the two. So alpha here is part of the qubit in the direction of 0, and beta is the part of the qubit in the direction of 1. In fact, the magnitude of alpha square is the probability of that qubit to be in the 0, and beta square, the magnitude of beta square, is the probability for that qubit to be in the 1. Right? So how much of the qubit is in 0 and how much is in 1, and as such, what's the probability that this qubit will eventually be a 0, or what's the probability that this qubit be a 1? That's one way to solve it, and we call this the standard basis. Okay, why? Because we are describing the qubit as the combination between two bases that is called the 0 and the 1. We call this the computational basis or the standard basis. Another way to describe this is in the Hadamard basis. Right? So the Hadamard basis, you describe your qubit as a combination of something called plus and minus state. The plus and minus state are just a superposition between 0 and 1. So the plus is 50% in the 0 direction and 50% in the 1 direction. Right? And the minus is also 50% in the 0 and 50% in the 1, but there is a phase in between. So these are the two bases. And when I say orthonormal, it means the following. Number one, 0 and 1 are orthogonal on each other. So you can think of this as 0 being the x-axis and 1 being the y-axis. They are two axes that are orthogonal, and your quantum state is a vector that is the combination between the 0 and the 1. Same thing for the standard bases, the plus and the minus. They are orthogonal. They are perpendicular on each other. Each one can serve as an axis. Okay? That's ortho. Ortho means orthogonal. And normal, because the unit length, or the length, sorry, of each vector here is 1, right? So any quantum state is actually has a unit length, a length of 1. Okay, so this is how we represent the data. So again, just to simplify things without looking into much of the math, I want you to think that the key difference between a classical bit and a quantum bit in an analogy to this coin example. If it is classical, as in binary data of 0 and 1, the coin is either head or tail. If it is quantum, the coin is spinning. So it's basically between the head and tail. And this is just what I'm showing here is how we describe this mathematically. Right? How can I describe this mathematically? So that's the data. Now, the second part is the operations, because now we have the data, we need to operate on this data. We need to do some computation, right? So the operations are represented by something called the quantum gate, right? We say that the input qubit psi n is applied to a quantum gate u, and this will give you an output qubit psi out, right? So I can think of this as this box here. It's a quantum gate. The quantum here is called x. I give it as an input, a quantum state. It will change this quantum state and create another quantum state. Okay, so this is an operation. Okay. This is, for example, one famous gate in quantum, which is called X, an X gate. Okay, so the X gate, what it does, if you give it an input quantum 0, it will change it to be 1. If you give it 1, it will change it to be 0. So this actually does a flip in the standard basis. So if you are in this standard basis representation, it will make 0, 1, and 1, 0. Okay. Another famous quantum gate is called the Z gate. So the Z gate will do this bit flip, but in the Hadamard basis. So if you give it as an input a plus state, it will change it into a minus state. If you give it a minus state, it will change it into a plus state. Another very important gate is called the H gate or the Hadamard gate. This gate makes you change from one basis to another. So if you are in the standard basis, which means you have the axes as 0 and 1, it will change it to be the Hadamard basis, plus and minus. So if you give it a 0, it will make it a plus. If you give it a 1, it will make it a minus. It changed the bases. But what is more valuable is that this gate actually create for you a superposition. Because if you give it a 0, it will change it into a plus. What is a plus? As I said before, a plus is a 50-50, 0 and 1. The plus state, if you write it mathematically, it's 50% in the 0 direction plus 50% in the 1 direction. Okay? So this means that the Hadamard gate, you can give it a state that is not in superposition, it's 0. There is no superposition here, just a 0. And it will create for you plus, which is a superposition 50-50 between the 0 and the 1. So it creates for you a superposition. These are just examples of some famous gates. Now, if you speak to a physicist and you told them quantum and qubit and quantum gate, then they will say, what do you mean by a quantum gate? What are you talking about? There is no such a concept of a quantum gate. And quantum gate means something for us, computer scientists and computer engineers, because we make the analogy to classical. In classical, we have all these gates, as I told you before, AND or XOR and whatever, and we create them with transistors. So we make the analogy and say, oh, there is something called a quantum gate, and it changes the state from the input to the output like this. But in reality, there is no quantum gate because these, for example, are not some transistors that is going to change the state from 0 to 1. No. What happens, like let's take an example of IBM Quantum. What IBM Quantum does, it creates a microwave pulse that will excite a qubit in the 0 state and make it become in the 1 state. Or create a microwave pulse to make a qubit in the plus state become in the minus state. Or a microwave pulse that take the 0 and change it into a plus. So it's just microwave pulses, some microwave pulses that will cause the qubit to change its status. Okay, that's why they say, what do you mean by a gate, right? But for us, we make the analogy of classical gates and quantum gates. Okay, so we have data, right? These are qubits. The key thing is that they can exist in superposition. We pass this data through a sequence of quantum gates. So here I showed you just one gate, right? But then you can have an X followed by a Z followed by an H and so on. And this is called a quantum circuit. It has lots of components and you can use these components in order to do some operations, right? This is what does the calculation. This is what will eventually generate a desirable quantum state that you can then get the result at the output. But then how can we read the result, right? Because in classical computers, I'll just feed my data to feed my data to some algorithm. It will do the computation, and then I read the display on my screen, right? How do we do this in quantum? In quantum, it's different. In quantum, when we want to read the results or do a readout operation, it's meant that we do a measurement. We measure the quantum state, right? Remember that thing about the coin, right? The spinning coin. When I told you that the quantum state, you can think of it as a spinning coin. And then I ask you, so what do you see now? You say, I don't know. I mean, it's just something spinning between 0 and 1. I said, no. Tell me what's the result. So then you have to stop the spinning of the coin, right? And when you stop the spinning of the coin will stop, right? So we say that it's a quantum state that collapses. So the quantum state will collapse. And now you read a classical value, right? So it was spinning between the 0 and 1, and then it collapses when you do the readout operation, and you read, is it head or tail, right? So you design your quantum circuit and the quantum algorithm in a way such that after these operations, say for example, your correct result will have a high probability of reading 0 or a high probability of reading 1, right? That's how you design your quantum circuit to get a specific desirable output. Okay, so the result, as I said, it's a projection. We just project our quantum state to a classical value of 0 or 1, your original axes, x of 0 and x of 1. And this means that your state will collapse. So you are no longer a quantum state that is spinning between 0 and 1. You will collapse and you do a readout operation, right? So that's the complete, I would say, chain. You have your data being qubits. The most important thing is that they are in superposition, which means they are between 0 and 1. The operations are described in terms of quantum gates that you are putting them in a specific sequence to do the algorithm that you want. And when the computation are done and you want to read the result, you do a measurement process. And the measurement will make you collapse from a quantum state to a classical value, and you do a readout operation. Now, one very unique thing about quantum is a theory that is called no-clone theory. No-clone theory, it means we cannot copy a qubit. right? As long as the qubit is spinning, you don't know what is the state, you don't know what is the value, and you cannot recreate another one like that and have two copies of the quantum state. You cannot do that, right? So in classical information, for example, I can copy a folder from one place to another place, and I have two folders now that have the same data. You cannot do this in quantum. In quantum, you cannot make a copy. You cannot create a copy. You just have a quantum state, and the only way for you to know what's the value of the quantum state is to measure it, and if you measure it, it will collapse, right? And you cannot make a copy of a quantum state. Now, this is, for example, why quantum is value and why everything I talked about here, quantum operations and so on, is that quantum actually can help you to solve very hard problem in reasonable amount of time, right? And this is quantum computing. So quantum computing can use the concepts of quantum mechanics, superposition, interference, and so on, and you design a quantum circuit that can solve a problem for you in a reasonable amount of time. So for example, consider the problem of key distribution, right? If you want to distribute classical keys between Alice and Bob, you have Alice and you have Bob, and they want to share a secret key so they can use it later on for encryption. One option is that Alice and Bob, they meet physically somewhere, like everyone have this diplomatic bag, a diplomatic bag, and it has the set of secret keys to be used. And then like the spy movies, they will exchange the bags, and then everyone go to their country and use these keys inside the bag to secure the messages from now on. But what if they never met? What if Alice and Bob never meet physically? So how can they exchange the secret keys from one to another? That's the question or the problem of key distribution. So there are existing classical key distribution protocols. One of them is called Duffy-Hellman key exchange protocol, where Alice and Bob will share some public parameters and then keep some parameters secret at their locations and then run an algorithm. And this algorithm, at the end of it, they will both of them come up to the same key K, right? So they will derive the key K from some shared parameters and some secret values following this algorithm, right? This is actually a secure algorithm. Why? Because if someone is eavesdropping on the channel and listen to the public parameters being exchanged on the channel, it cannot still solve and figure out what is the key K. Why? Because it needs to solve something called the factorization problem. And solving this factorization problem, when we say that B is a large number and A is a large number and so on, it's very hard to solve this problem with a supercomputer, a classical supercomputer in real time. It's very difficult. Even if you are eavesdropping and you are listening to the public channel and you know what are the public parameters, you cannot solve this factorization problem here and come up with the same key K that Alice and Bob know in reasonable amount of time, okay? That's with classical computers, but quantum computers can actually solve this factorization problem in reasonable amount of time and in fact break the key. So they can know what is the key value K if we have a powerful enough quantum computer. Because there is an algorithm, this algorithm is called Shor's algorithm. It's a quantum algorithm that when you run Shor algorithm, you can solve this factorization problem with a quantum computer in a reasonable amount of time, okay? So this is the part where quantum computing is a threat to cybersecurity. And so Shor algorithm, like the quantum circuits that I have shown you, you will design an algorithm that use quantum circuits to design something called quantum Fourier transform, quantum phase estimation, quantum period finding, and then at the end, you can just solve the factorization problem and you figure out what is the key. Now, these numbers, there is lots of exaggeration in the numbers, and I couldn't find a source that can really be trusted that these are the real numbers. But let's just, for the sake of approximation, classical computers, you would require 300 trillion years to break an RSA that is with 2048-bit encryption key, right? So this is not a reasonable amount of time. I mean, no one can solve this problem in a reasonable amount of time and figure out the key. But if you have a quantum computer and it has more than 4,000 perfectly stable qubits, you can break that in a matter of seconds, right? Just again to get a sense of, oh my God, I mean, this is crazy. But I want you to know two things. Number one, we don't have this yet, a perfectly stable qubits, right? So this is the current quantum computers that we have, they give you noisy and unstable qubits. That's number one. And number two, this number, again, we don't have that number of qubits in one quantum computer. That's big, right? So we don't have that number of qubits and they are not perfectly stable. Currently, we are in something called NISQ era. NISQ means noisy. That's the N. Intermediate scale quantum computer. So current quantum computers are noisy. They are not giving you stable qubits, and they are intermediate scale. The largest that I have seen from IBM Quantum is just 1,000 qubits. Right? So we are still not there yet. But in theory, if we are there, if we have enough number of perfectly stable qubits, we can break these RSA algorithms with Shor algorithm, and we can just break the key. Okay. And as I was saying here, we are not there yet. Current state of the art, we don't have enough qubits, and the error rate is pretty high. So we are not there yet in terms of the implementation, but we are there in terms of the theory. Theoretical, we can do it. Okay? So that's the threat, right? What I showed you here is the threat of quantum computers. But also there is an advantage, which is something like quantum key distribution. You can use quantum technology to exchange secret keys in a way that is unconditionally secure. You're not setting conditions, which is computational complexity like Duffy-Hellman key exchange. No, you can come up with a way to exchange secret keys such that you are confident that there was no eavesdropper. No one else has the key. And this is called quantum key distribution. It was BB84. It was in the year of 1984. These two scientists, they come up with this algorithm. All it requires is one-way quantum channel between Alice and Bob, and two-way classical channel between Alice and Bob, and they can exchange a secret key using the quantum channel, and they can be very confident that no one is dropping the channel, right? The quantum channel doesn't need to be secure, as in I don't need to have any encryption on the quantum channel, but the classical channel, I just want it to be authenticated. I just want Alice and Bob to know for sure that this is Alice and this is Bob. They need to authenticate each other. And this algorithm would work very well. The concept is the following. This is a quantum circuit, right? So this is the qubit, the input qubit, and then it goes to an H gate, and now you have a plus state, right? So this is a superposition plus. This is at Alice. If Alice create a plus state and send it to the other side to Bob, Bob apply another H gate, it will cause this plus state to become a zero. And then the zero, when you do a measurement, it will read zero, right? That's if Alice and Bob don't have anyone in the middle eavesdropping the channel, right? So Alice will prepare a qubit in one basis, and Bob will measure the qubit in the other basis, and that's perfectly fine. So what Alice can do is randomly creating, like with a seed with a random number, create random quantum states and send it to Bob. Bob will do random measurements, right? And then they will just announce what are the bases of encoding at Alice and measurement at Bob, and they will come to the secret key. There are lots of details here, and for the sake of time, we won't go through all of them, but there is a complete description of quantum key distribution if you go, for example, to Qiskit textbook. So the Qiskit textbook is done by IBM Quantum. It's an open source, an online textbook. They have the code. They give a video to describe the process. It will give you all the details. But what I want to say is there is a way that Alice and Bob can share a secret key, and this secret key will be secure, right, to eavesdropper with 100% probability. Because if there is an eavesdropper on the channel, remember I told you that the quantum state has to collapse, right? And when the quantum state collapses, Bob will know. Bob will know that something went wrong. Someone was on this channel eavesdropping, and because of that, Alice and Bob cannot come up to an agreement on a secret key. And this will be their indication that someone was on the channel. This is a key distribution process was insecure, and when they know that, they can just abort the channel and try to do quantum key distribution on another safe and secure channel. So this quantum key distribution process, again, as I said, Alice will randomly encode quantum states, and Bob will randomly do a measurement, and then they will announce the bases used for encoding, the bases used for measurement, and when there is an agreement, they will say that this is our key, right? If, as I said, there was an eavesdropper in the middle, they will never come to a key agreement, and this is their indication that someone was on the channel. This is unconditionally secure because here I didn't make any computation assumptions. I didn't say, oh, but the problem required the quantum computer of the eavesdropper to be that much good. No. There is no. The only thing is to leak the key if you can break the law of quantum mechanics, and you cannot do it. You cannot break the law of quantum mechanics. It's the law of nature, okay? So this is no unconditionally secure. We don't make any assumption on computational power like Duffy-Hellman, which is the classical algorithm, for example. So what I want you to just get from here is the following. While quantum computer can be a threat, it can break encryption and classical keys and can know break Diffie-Hellman key exchange and as such it's a threat to our current encryption system. With it also comes the promise I can exchange secret keys in a more secure way, and this is the good angle or the advantage of quantum technology. Okay. Any questions so far? So before I talk a little bit about quantum communication. So what we talked about is quantum bit, which is being in superposition between the 0 and the 1. Quantum gates, input quantum state. It will do some operation on it and give you an output quantum state. When you want to read the result, you do a measurement. This is dangerous if you look at it from computing. It can solve very hard computational problems and as such can break encryption keys, for example. But also it can give you something good, which is a secure way to exchange keys. That's what we discussed so far. Any questions so far?
Yeah, there is a question. Yeah.
Wait, sorry. So you talked about like the superposition concept as like a spinning coin. How do you,
Yes.
when the state collapses, how do you know which side of it is 0 or 1?
Yeah, because you do, now you observe the system, right? Again, let's go back to the analogy. So when you have this spinning coin and you stop the spinning, it will fall to one of the sides, either the head or the tail. When it falls, you just observe the system and you can tell this is a 0 or a 1. That's what we call it a measurement operation. So you do a measurement and you try to figure out is it a 0 or a 1. We call it that you observe the system, right?
So this quantum system is like slowly pushing it towards like maybe heads or tails to get an accurate result.
That's correct. That all these quantum gates in the middle, they are making these changes to make it more probable to get a specific quantum state at the output. And this specific quantum or this classical measurement at the output, this classical measurement at the output is tied to something that you want to accomplish. I can, for example, advise you to read something that is much simpler than Shor algorithm, because Shor algorithm is pretty complex. If you read something called Glover algorithm, Glover is a search algorithm, right? So you have an unsorted list of so many items and you want to come up to a specific item, you want to search for it in a very small amount of time, right? So it will always tell you that the winning item will guarantee an output of, let's say, 0, 0 at the output. So when you do a measurement, it will always give you 0, 0 at the output. And you say, that's the item I'm searching for. So you design the whole algorithm such that if it gives you a specific measurement result, then that's the correct answer, right? So that's how you design an algorithm, right?
Does the quantum key distribution works even though there's no communication theorem? It's not using them for communication, so it's something else?
Can someone repeat the question? I couldn't hear it.
Can you speak a bit louder?
Yeah, so the no communication theorem, the key distribution works even without like communicating, like using the qubits.
Do you mean the no clone theory?
No, let me see. Actually,
No communication theorem was what he said.
yeah, no signaling principle, no communication theorem.
Yeah, that's right. Yes. This is still work because, as I said, all Alice and Bob need to do is Alice need to encode the quantum states at random and send them toward Bob, and then Bob will do the measurement at random, right? And this worked perfectly fine. I mean, there is no, how can I say, nothing here to conflict with the no communication theory. Yeah.
Is quantum computing deterministic all the time? So you like
No, it's not. It's probabilistic. So we have to do the measure. That's an excellent question. So you would see, for example, if you run a quantum circuit through a quantum computer, you need to run it, let's say, on IBM Quantum 1048 times, and then you get the probabilistic output of what was the 0 and the 1. You can design your quantum algorithm to have specific output with a probability of 100% and other output with a probability of 0%, but it's still a probabilistic process, right? So it's a probabilistic process, and you need to repeat the measurement so many times and look at the histogram of the output to see what's the result. It's a probabilistic process. Yeah.
Probabilistic. So when you run it more, it becomes more accurate. Does that follow like any trend? Is there like a specific amount you want to run a specific quantum algorithm for?
Another excellent question. So, for example, Grover algorithm that I told you, it's a search algorithm, Grover algorithm. This one, it needs, yes, a specific number of runs to get you the correct answer at the output. Yes, you need to repeat the algorithm specific number of times, and if you did it less than this number of times, you will not get the correct answer. So you need to repeat it repeatedly, apply some part of the quantum circuit, which is the oracle and diffusion operator. You need to repeat these specific number of times, and only then, if you repeat them the number of times, you get the correct answer at the output. Yes.
So for any arbitrary algorithm, could you calculate how many times you need to repeat it?
Any arbitrary algorithm can do what?
Could you calculate how many times you need to get to a satisfactory result?
So again, it depends on what is the design part of the algorithm, right? Like for example, whatever I described for you here as a QKD, it seems as you see they match at some point and they don't match at another point, and because of that, this big part of the message that we communicated need to be discarded, right? So let's say, for example, I want my key length to be 1000 bit string. Then I need to transmit roughly 2000 quantum state from Alice to Bob. So again, I know that I have to repeat this or transmit this signal 2000 times. So eventually I get a 1000 key length, right? When I was talking about Groover algorithm, I know in order for me, for example, to search this list, I need to repeat this operation 2 times, for example, to get the correct answer. So again, it depends on what is the algorithm that you are designing and some of the criteria that you consider it to be a success for this algorithm. Yeah. Okay.
Got a question. So I'm not very familiar with this, but I just on an observational basis, I see that like comparing the key beats that Alice sends and Bob receives, I see that where we have like the 0 and a 0 on both ends, we still have a cross and not a check. I don't know if that's maybe based up. I think the third to the last one, like the 0 key beat from Alice and 0 that Bob receives is still a cross. Is that something unique to like quantum computing, or is that just, I don't know if you know the third one or third to the last, the one that's not under the green box. So Alice has a 0 qubit, and then Bob has a 0 qubit, but it's still a cross on a check. So I think that's, you see it?
I couldn't hear that.
Yeah, so if you look at the third column from the end,
Yeah.
there is, I think, both of them have got the same one, but the X and green kind of check marks. For that particular one, you had an X. I don't know if this was fictitious or you, maybe you can.
Not the
Yeah, maybe
Maybe there is a typo here, but what in concept or in principle, if the
Yeah.
encoding basis and the measurement basis are the same, right?
Yeah.
Then we say that's a match and this is part of the
Yeah.
key. So for example, this is diagonal and this is also diagonal, so there is a match. This is vertical and this is vertical, there is a match. This is diagonal and this is vertical, there is no match, this won't be part of the key. Okay?
Yeah.
So whenever the encoding basis and the measurement basis, this one here is the encoding basis and this one here is the measurement basis. When they match, when the encoding basis and the measurement basis match, we say that this is part of the key. When they don't match, this is not part of the key. Okay, so if there is a typo in the final key that I write here, that's my bad, but you get the concept now, right?
No typo, you're fine. You can continue. I think you've had entertained a lot of questions. You can maybe
Okay, yeah. So just moving on, there are a couple of interesting concepts now, which is called quantum entanglement and quantum teleportation, and this will bring us to the concept of quantum internet. And probably due to the time, we'll stop there. But I can show you some of the papers that you can read about the topic. So we said before that quantum is very unique in some principles. One of them is superposition. Another very like fascinating thing about quantum is entanglement, right? So that's another unique thing about entanglement that you would never find in a classical system. So what is entanglement? Entanglement is a phenomena in which you have two pair of quantum states. So you have one qubit and another qubit, and both of them will be generated in a way such that if you measure one quantum state, it will affect the state of the other quantum state, right? So think of this as you have two boxes, right? These are two boxes, and each box has a ball, and this ball represents a quantum state. And let's say that these two are entangled. So the two balls, they have this entanglement relationship between them. This means there is a correlation relationship, which means if you measure this ball, if you see this ball to be red, then the other ball must be either red or yellow, but you know for sure, right? So for example, if one of them open the box and do a measurement and find that the ball to be yellow, then the other ball must be yellow. It must be. I mean, it cannot be anything else. If this one open the box and find the ball to be red, then the other one must be red, right? So there is a relationship, there is a correlation between these two qubits, and we call it an entanglement. These two are entangled. If you measure one of them, you know for sure what is the status of the other one. Now, at the time of Einstein, he called it the spooky action at distance. Why? Because if you have two quantum states, right? One of them is in the USA and the other one, let's say in China. You see the distance between them? Huge distance between the two. But still, if you measure this one here, it will affect the result of this one here, right? Now, can we use this to transfer communication? The answer is no, and that was the question of your friend over there when he asked me about the no communication theory, right? That's the no communication theory. I cannot use this by itself to communicate. Why? Because the state of this quantum is random. I don't know. Always our information is contained inside the qubit, and if it is completely random until measurement, I don't know what I'm communicating, right? It's like I want to tell you something that I already don't know what it is. I don't know what it is. What I'm really telling you, I'm not communicating anything to you because I don't know what I have. The only way for me to know what I have is to open the box, observe the ball, and now the quantum state will collapse, right? We don't use this by itself to communicate, but this can be used as a part of the communication process, right? So anyway, what I want to say is there is a phenomena. This phenomena is called the quantum entanglement. This happened between two quantum states. One of them will be with Alice and the other one will be with Bob. If they are both entangled, this means if Alice measure her qubit, this will determine the measurement status of the qubit at Bob. So if Alice find this to be yellow, Bob for sure will find it to be yellow. If Alice measure this to be red, Bob for sure will find its qubit to be red. Okay. One example, a very famous example of this entangled state is called the Bell pair, right? So Bell pair, this is the general form of a Bell pair, and you can find all of these are called, each one is an entangled state, right? So you have two qubits because you say 0, 0, 1, 1. So this is everything you see in red is the qubit with Alice. So Alice will have a qubit that is a superposition between 0 and 1, which is the red one. And Bob will have another qubit, which is a superposition between 0 and 1. And this expression here describes the two qubits together, right? Both qubits together. So this is, as I'm saying, this is Q naught, which was Alice, and this one is Q1, which is with Bob. Now, if Alice measure its qubit to be 1, then for sure Bob will find its qubit to be 1. That's it. There is 100% certainty if this one measured to be 1, the other one will definitely be 1. But if Alice measure its qubit to be 0, then Bob for sure will find its qubit to be 0. So if these two are entangled, then 100% if Alice measure its qubit to be 1, Bob is for sure 1. If Alice measure it to be 0, Bob is for sure 0. Now let's take another quantum state like this one. So here, for example, if Alice measure its quantum state to be 0, in this case, Bob for sure will measure its state to be 1, right? And if Alice measure it to be 1, Bob will measure it to be 0. Let's take another quantum state here. If Alice measure it to be 1, Bob will measure 1. If Alice measures 0, Bob will measure 0. The last one, if Alice measures 0, Bob will measure 1. If Alice measure 1, Bob will measure 0. Okay, so this is called entanglement, right? So this is a special case of a quantum state. And you can create a Bell pair with a circuit like this. All you need is these two qubits. You take one of the qubits, pass it to an H gate, and then do something called the control knot operation, and this will create for you the entangled state, right? So this is the analysis of the circuit, but this is something that you can create easily in a quantum computer, for example. Now, why this is useful? As I said, by itself, entanglement cannot be used to pass communication. So that's the no communication theory. I cannot just use entanglement to communicate. But I can use entanglement as part of something called quantum teleportation, which is what we use for communication. So if Alice wants to send quantum information to Bob, this is Alice, right? And this is Bob. And when Alice has a superposition between the 0 and 1, think of it as a spinning coin. That's what Alice has. And Alice doesn't know what is alpha and beta. Alpha is the probability of measuring 0 and beta is the probability of measuring 1. And this is the information actually, alpha and beta, right? So this means that Alice wants to send to Bob what is alpha and beta, right? So what happened is that, as I said, Alice doesn't know what is this state, because if it knows what is this state, it means it measure it, and if it measure it collapse, right? So any measurement will collapse the state. And Alice cannot make a copy of this state, right? It cannot make a copy of the state and send it to Bob because there is something called no clone theory. So what happened is the following: Alice will teleport alpha and beta to Bob, and the state at Alice will collapse. So at the end of the teleportation, Alice will not have the information. The quantum state will collapse at Alice, and Bob will have that information, will have alpha and beta. Okay? And this is done not by sending the quantum state through, for example, a fiber link. So Alice is not going to send the quantum state to a fiber link. No, Alice will do some operations and then the information will appear at Bob. So when we say we do a teleportation here, we teleport the information, right? We teleport information, okay? So this is called the quantum teleportation. How does it work? You have Alice and Bob. Between them, there is a classical channel, not a quantum channel, right? And then there is a third party. This third party is called entanglement distribution entity. It is an entity that will distribute entangled particle between Alice and Bob. And this means that this party has a channel with Alice that is quantum channel that you see here in red, and another channel with Bob that is a quantum channel also in red with Bob. But Alice and Bob don't have a quantum channel. They have a classical channel, right? Now, what will happen is that this is how the protocol will work. The third party will distribute entangled quantum pair, one half to Alice, one half to Bob. So Q1 will go to Alice, Q2 will go to Bob, and these are entangled pair, okay? So these two, they have entanglement between them. Now, let's say that this is the information that Alice wants to send to Bob, right? So this is the qubit to be teleported to Bob. What will happen is that Alice will do some operations between Q1 and the Q node, right? So do some operations on these two, Q1 and Q node, and then send the classical information, which is the outcome of the measurement, send the classical information to Bob. And then Bob will use this classical information to apply some operations on Q2, and then Q2 will transfer to become Q node, right? So you see here that Alice didn't send the Q node, Alice sent measurement result of some operation on Q node and Q1, right? And this transferred Q2 at Bob to become Q node, the information that Alice wanted to send to Bob. This is the quantum circuit that can do this. This is the first part where you create the entanglement at this third party entanglement and send one part to Alice and one part to Bob. This is the second part where Alice do some quantum operation on Q node, the information that it want to send with Q1, which is its part of the entanglement piece. And then Alice do some measurement operation, as I said, and send this measurement operation, as you see here, to Bob. Then Bob will apply some quantum gate operation on Q2, which it has, and this will transfer Q2 to become Q node. This is called quantum teleportation. There is another interesting concept which is called entanglement swapping. So let's say I want Charlie and Bob to have entanglement between the two, right? But there is the third party entanglement cannot reach Charlie. I mean, it's not that far away, cannot reach Charlie. So what will happen is that the entanglement part will share half of the entanglement pair to Alice, another half of the entanglement pair to Bob, and there is another third party entanglement that will share an entangled piece to Charlie and another entangled piece to Alice. And then Alice will do something called Bell state measurement, which is an entanglement swapping. So it will swap the entanglement that it has with Bob and the entanglement that it has with Charlie. And at the end of the operation, these two will be entangled, right? So they are now extending the entanglement distance, right? And now Charlie and Bob have entanglement pair, and now they can do teleportation, right? This brings us to the concept of the quantum internet, right? So the quantum internet is, in its essence, is an entanglement distribution like network. So this is a network to distribute entanglement. If you distribute entanglement, then you can do distributed quantum computing. You can do secure communication, and there is something called entanglement-based QPD, and you can do sensing because you can do now distributed sensing. So the quantum internet is basically distributing all these entanglement, right? So it does in global entanglement distribution. Is there now a quantum internet? The answer is no. There is no such a thing as global entanglement distribution. There are some efforts, for example, from China through satellites to distribute quantum keys between Alice and Bob, but this is necessarily not an entanglement. There is an ambitious project in European Union called EuroQCI, where they will again distribute quantum keys among the states of the European Union. But again, all these things are not meant to distribute entanglements. They are just meant to distribute keys. So they do quantum key distribution. So we can say that the existing efforts, they support the quantum key distribution, but they cannot do on-demand entanglement distribution, right? And as such, you cannot also do entanglement swapping and figure out a path from source to destination so you can entangle two far apart entities together, right? And so, because of sake of time, we're not going into details. We proposed in our research a network. This network use satellites, use drones, and use ground layer. So we call it space, air, ground quantum network, SPARC. And we use this to distribute entanglement. And we use this to figure out an entanglement path between two entities. Let's say this is Alice, this is Bob. And then they figure out the yellow path to be the path for entanglement distribution. And at the end of the process, these parts can be entangled. If they are entangled, they can do teleportation, they can do secure key distribution that is entanglement based, they can do sensing, they can do whatever they want to do in a secure way. We did this entanglement distribution with reinforcement learning. So we trained an agent to be able to figure out the path between the source and the destination. And we come up with some protocols and policies. And we tested this. Again, for the sake of your, I'd say, session or this session, it's enough that you have known a quantum bit is a superposition between 0 and 1. We use something called quantum gates to do the operations. To read out the results, this is called the measurement operation, right? Quantum can be a threat because it can solve NP hard problems in reasonable amount of time. One example is solving Diffie-Hellman key exchange, like the factorization problem and breaking the secret key. This is frightening for security application, but by the way, it's good for some other optimization problems, like for example, drug discovery. This is something that can do drug discovery in a very good amount of time because it can solve difficult optimization problems in short amount of time. But as I said, it's a threat for security. But also it has a promise because you can use it for secure key exchange. Now, there is something or a concept that is called the quantum internet. What is quantum internet? It's just a network that distributes entanglements. If you distribute entanglements, then you can have two parties to do teleportation. They can do distributed computing. They can do distributed sensing. They can do secure key exchange. And this brings the problem of, okay, how can I figure out a routing path to route this entanglement from source to destination? If you are interested, you can find my Google Scholar and you'll find the papers over there talking about quantum and SPARC and how to do entanglement distribution and routing in a quantum network. There are other papers that we have about quantum identity authentication. We also have other papers on how to upgrade a classical power system network to support the quantum key distribution and quantum cryptography operations. It's a very fascinating and interesting field. I get into this field in 2018, 2019, and basically because everything I heard about it sounded like a black magic, right? It doesn't make any sense. This is not classical way of doing things. This is very weird. And because it's weird, I started to read more about it. And I want you to know that there is a great resource, which is IBM Quantum. You can access a quantum computer through the cloud, right? So go to IBM Quantum, create an account, and if you are a US citizen, because it will ask you this question, are you a US citizen? If you are a US citizen, you get 10 minutes for free every month to get access to a quantum computer with 127 qubits, right? And the reason I'm telling you that is they also have this Qiskit online textbook. So you can get in there. They will give you from the very basic fundamentals, like the foundations. You just assume you don't know quantum. So they have videos to explain to you what's quantum, what's a quantum algorithm, what's a qubit, what's whatever. And then they give you a quantum algorithm and they show you the code of the quantum algorithm with a language called Qiskit. This is Python based. And you can run the algorithm, as I told you, on a quantum computer, and you see it's working. So everything that I showed you here about quantum teleportation, Groover algorithm, Shor algorithm, you can actually run this on an actual quantum computer. You just access the quantum computer through the cloud, and you have 10 minutes. And this is enough, by the way, for small problems. 10 minutes is reasonably enough for you in a month to run some quantum algorithms and just see how does this world look like, right? Just to get you interested and excited about the topic. We teach here quantum fundamentals, 4,000, 5,000 level course, and computing and security and quantum AI because there is quantum machine learning. And our students, we have them to use the IBM quantum computer and run some algorithms and write codes I encourage you highly to look into Qiskit and IBM Quantum. Yeah, that's all. Thank you.
Thank you very much.
Any questions? Do we
Yeah,
have
so
time for questions?
let me take if there is burning question one or two. You had taken, Mohammed, a lot of interesting questions in the middle of your talk, so I
Yeah.
wouldn't worry much if people don't ask.
Very good.
If you don't mind, if you share your slides, then we can post it so that they can follow along on some of the other
Absolutely.
things you didn't talk about. But you
Sure.
did a great job the last time talking about quantum computing in 10 minutes, and when you were given 50 or 55, you did an impressive job, and I'm sure there are many people here who would be curious to find out more. And thank you for
Very good.
mentioning
Sure.
those resources that are available. I know you were traveling and you made the time. So
Yeah, yes. It has been a very interesting 2 weeks.